So, yeah. So, welcome to the third session of the XAIDA Webinar series. Today, so we are welcoming José Tárraga, who is a PhD student. Yeah. So, welcome to the third session of the XAIDA Webinar series. Sorry. At the Internal Displacement Monitoring Center and at the Image Processing Lab of the University of Valencia. So, José, you are presenting your work on interactions between socioeconomic context and natural hazards on human population displacement. And so all the reference are on the webinar page on the XAIDA website. Please, José.
So, hello everyone. I don't know if this will become a problem, but actually Fallas is going crazy in Valencia. Excuse me for the noise. I don't know if you can hear me.
It's fine.
But that you can hear me. Maybe the noise cancellation works, but I have to shout a little bit. So excuse me for that. I don't know. Okay. Yeah. So maybe we can wait. Just it stopped. It works. Okay. Sorry for that. Can you see my screen, right?
Yes.
Can you see? Are you seeing the presenter notes, or are you seeing the presentation?
The presenter notes.
Right. So, just excuse me. Yeah. Sorry for that. Okay, so yeah, today I'm going to talk about how we employed some explainable AI methods to explore the interaction between hazards and socioeconomic context on human population displacement. And this is some work that was developed with the University of Valencia and in collaboration of IDMC, the Internal Displacement Monitoring Center. Basically, the ISP, I think that you know it, but it's a group that specializes on employing advanced machine learning techniques to explain climate phenomena, but also very recently socioeconomic impacts of climate. And here we studied human displacement, which is a big phenomena that we need to pay close attention to. I'm going to start my talk by talking about displacement, particularly displacement risk, how we tackle the displacement risk for sudden onset hazards on our global level, and a very few points on how we are moving forward to better refine the methodology that we employed. So first of all, a little bit of context. Disaster displacement refers to people that have been pushed to leave their homes as a result of a hazard to avoid the impact of, or because they already received the impact of a hazard. And the magnitudes of disaster displacement during these few years have been huge. IDMC estimates that there are 32.6 million people that have been internally displaced due to disasters, and this is the most common form of human mobility in the context of climate change. And we also have to take into account that of all disaster displacement events, 98% of those are triggered by weather hazards, and they pose very severe economical and human consequences for the people that are not prepared in these situations. So there is this huge framework that has been recently being pushed in the humanitarian and anticipatory action setting. And there are a lot of papers and methodologies that are saying that anticipatory action can actually help mitigate human and economic loss in the face of a disaster. So the thing is that as soon as you have early warning signs or you have any sort of alert of a shock event, if you anticipate or you act on the event before it happened, it can actually be very beneficial, or can anticipate and reduce losses because of these disaster impacts. However, there are many steps in this early warning chain in which you run from observation until you decide. All of these are some of these steps, and all of them could benefit from some kind of machine learning approaches. I think that's something that we have been working in ISP. And we are looking, today we are going to look about particularly this node, which is impact forecast or explanation about how we can use models to explain vulnerability, exposure, and hazard that compound to displacement risk due to disasters. So this is something that we know. Climate change will increase the frequency and intensity of this weather-related hazard, but it's not the only factor that drives displacement. And this has been highlighted first by IPCC in 2014. You have a compounded risk in which you have the hazard, which is the phenomenon that may cause displacement. You have the exposure, the people that are living in that area, and you have also a vulnerability factor that is relatively difficult to quantify correctly because it depends on a lot of socioeconomic factors, and some of the causal relationships that are within this vulnerability node are not unclear or are indirect. So what we did here is to try to account for all these three dimensions of displacement risk in our study. And for that, what we did was basically gather a database focusing on sudden onset disasters. These are floods, storms, and wet mass movements that trigger the displacement of populations worldwide. And as we know, these are very complex systems. All these terms interact. It's a very multidimensional problem, and the functional relationships between the variables are actually unknown. And there are increasing efforts on quantifying these relationships, but still the field is really early. So what can we do from a data-driven perspective? We could employ some of explainable AI techniques and some of these nonlinear and models to uncover the main drivers of interactions between all these components of risk and actually human mobility due to climate change or displacement or any kind of target variable. But here we are going to focus on displacement. I'm going to talk about the study that we published in Nature Communications at the end of the year. And firstly, for studying from a data perspective, of course, you need data. And here what we did was basically build a geolocalized disaster displacement database. So what you can see here is that we built around 2,400 displacement events and from different countries around the globe. And you can see that different geographical regions were impacted differently. You can clearly see the impact of monsoons and floods in Philippines and India. And also we can see that floods in Africa have a huge impact. So once you have these, we have this data set built or identified, we decide to target displacement. I'm going to tell you a little bit about IDMC. So IDMC has a UN mandate that specifies that they should collect all information related to disaster displacement, but also conflict and violence displacement. And what they do is basically an organization that dedicates to compile and curate data. And they have these monitoring systems, and we also have these curator data systems that allow us to deploy the most quality data sets about disaster displacement. And of course, there is no lower threshold on displacement. All figures from news to humanitarian reports to disaster reports are reported. So once we have this target variable, what we did was to geolocalize all of the disaster displacement events on a global level. Each one of these polygons correspond to a disaster displacement event. So we have a database that we can exploit to actually investigate the effects of disasters on displacement. And then once we have these polygons extracted and the displacement data aggregated to these polygons, we harmonized this displacement risk coverage to this data. And we selected, first of all, we selected around 60 socioeconomic variables, and we collected those, and then we discarded those based on correlation test or redundancy information. And then We tried also to minimize and to account for the sufficiency hypothesis. All the relevant drivers had to be included into the analysis. And then we built this list of variables and harmonized hazard, exposure, and vulnerability covariates. For example, we have here the absolute wealth index, which is a socioeconomic index of poverty. We also built, we gather precipitation variables from Area 5 land and from wind speed, NDVI, also population. Human modification, this layer, human modification layer, is about, let's say, construction and how well built is an area, and then other variables such as elevation, conflict, and area. And then also we harmonized some SDG index such as the education expenditures and percentage of agricultural land to each polygon. And once we have this database ready, basically what we did was to train random forest models and to train gradient boosting machines models. We decided to go with these because this is a very high-dimensional, no-linear problem. There is tons of variability, and we also feed it linear regression models, and you can see that the performance is way worse. And so once we have these models feed, what we also looked at is, okay, let's look at how weather variables are explaining these displacement data from the models. And what we observe is that when you include all the exposure and vulnerability variables, you actually predict much more displacement data points. And this is where, let's say, canonical or conventional analysis of machine learning would end, or if you want to end with a predictive models, this is where the thing would end. But the question is, we can use these models to learn from the models. And that's what we did here. Basically, we employed Shapley values, which is a very widely method to measure or to understand how a model has learned or how different variables contributed towards explaining the model outcomes. And the nice thing about Shapley values here is that each point corresponds to one of those polygons of the disaster displacement database. And they allow you to measure which is the importance that the variable had in explaining displacement, but also the direction of the interaction. For example, here you have the Shapley ranking of the random forest values, random forest models. And for the precipitation variable, what you have in each point is that greater values of precipitation allow the model to predict greater displacement values. For the absolute wealth index variable, which was the socioeconomic poverty level index, what the model is telling you that lower absolute wealth index values, poorer households actually help the model to explain greater displacement magnitudes. And you can run this analysis through all your covariates, through area, fatalities due to conflict, education expenditure, etc. So actually, it's a really powerful tool, in my opinion, to dissect how variables are interacting with each other. And of course, in all of these explainability techniques, you should fit different models and you should try different approaches. So we also trained the gradient boosting machines. And what we see is that in the three main variables, are coincide in both models, right? So you have in the gradient boosting machines, you have area that is more important than precipitation and absolute wealth index, but the direction coincides and makes sense with what was known in literature. And once you have these Shapley values, you can run also different scatter plot analysis to actually investigate on this question of the differential vulnerability, which is something that popped up in literature quite a lot. It's the concept that given the same disaster impact or the same exposure, you will have different magnitudes of displacement or of economic damage, etc. So this is something that we visualize here with our models. These are Shapley dependency plots in which you plot Shapley values in this axis and the precipitation values in the x-axis. And then here what we feed is averages for any variable that you would like to investigate. Here we investigate the absolute wealth index, and what we see here is that for the same precipitation value, poorer households actually depict greater displacement magnitude, and on the contrary, richer households depict less displacement magnitude. And for the area, you have this similar relationship, and it's a very nice way to quantify it and to visualize this differential vulnerability impact from data. Moreover, we also feed it causal forests. So we know that Shapley values are not actually estimating causality or inferring causality. So we also decided to go for these causal forests to estimate the average causal effect. And this is on the potential outcomes framework. And you compare basically which is the different outcomes of the different treatments. Then these causal forest algorithms are fit to maximize the average conditional treatment effects. And what we see is that these are in agreement with the Shapley values rankings and the absolute wealth index variable, meaning that they have the precipitation has a positive causal effect on displacement, and the absolute wealth index has a negative causal effect on displacement. So these are all also tools that you could use to investigate the factors that are driven by So to conclude about this paper, what we did basically here was to provide empirical evidence about which were the different interplays between the factors affecting disaster displacement, and we provided evidence that it was mediated by interrelated set of factors, right? We provided evidence on these weather, exposure, and vulnerability factors, which all of them popped up in the Shapley values analysis. And we also were able to map this differential vulnerability concept that was appearing in literature and visualize it, which is, I think, a pretty nice contribution. And the thing is that IDMC is keeping improving their data, and as we have this data, systematic data collections, we can train data-driven models to actually forecast and do anticipatory action studies on displacement data. And we also can use these algorithms. The explainable AI branch of ML brings these kind of opportunities to understand mobility patterns, to perform risk mapping, or to inform early warning systems. And as future work, what we need to do is to increase spatial resolutions, to characterize better the climate screens, also to enhance the vulnerability dimension, which has a lot of components. No? So I'm going to talk very briefly about how we are moving forward, how we in IDMC are moving forward towards these, improving these databases and improving the characterization of impacts of disaster on populations worldwide. And one of the projects is the historical data revision. And this is basically because all the displacement data between 2008 and 2016 is not in well shape to be delivered to the user. Basically, what we are doing is to build a document processing pipeline in which we parse PDF information from historic reports, from humanitarian organizations, from news outlets, etc. And then we are using LLMs to actually retrieve the information, and then we evaluate those LLMs, the prompt and the classification with the annotated data that IDMC has. And we are able to retrieve about 15 data files from heterogeneous documents, which is actually one nice application towards having accelerating the annotation of datasets and gathering of datasets in any disaster context. Yeah, so you can see here some examples. You have documents, and you basically retrieve a CSV file using this pipeline that we are developing. And then you have the ability to annotate the PDF, so a manual reviewer can go through this to actually deliver the data in a correct way. Another module that we are developing is the geolocation of disaster displacement data. So that was one of the weaknesses of our study, I would say, because the areas are very heterogeneous in the polygon levels. So there is a need to actually geolocate displacement in a way that is standardized, that can be used with interoperability. So we are improving this, and we are with the motivation to deliver these precise disaster impact locations. and also accounted for contested and disputed territories which could raise political issues. We are building this Python package, which allows you to, from a locational name, actually have a polygon in which you can harmonize your data to or analyze the climate anomaly, etc. And here it's a very brief methodology, but we basically leverage 2 different geocoders responses, and with a set of rules, we are able to extract the most precise location from text. And then we standardize to this polygon, we retrieve codes to be able to compare with the standardized datasets, which will allow you to act in an operational level. And then if there are entries that need to be manually revised, we can flag those and correct them manually. We also validate our methodology with these standardized datasets, and it's actually an improvement because when you try to geolocate data, most geocoders actually deliver you their location according to their own internal ranking. So this is a nice package that we are developing to actually deliver you an administrative level unit that you can standardize, right? And then we have also this project in mind that since you are attribution climate stream experts and you work a lot of climate attribution information, we want to highlight that 45% of the displacement that occurred departed from the long-term average trends. So we have a lot of displacement that are driven by climate anomalies or are being disproportionately impacted by these climate anomalies. So we actually want to provide with our dataset information on which of these events and how much these events were caused by climate change. And this is something that we would like to hear your feedback you can contact me later if for any reason you're interested in this topic. And that would be all. Thanks a lot for attending and for listening to the talk. I can answer any question that you have, or if you want me to delve particularly in any topic, I would be happy to do so. I think the fireworks stopped, so it's a nice opportunity to ask questions.
Thank you. So please go ahead in the chat or in the...
I have a question, comment, Manon, again. Thank you, Jose. It looks like there is a big party in Valencia, so sorry, it's a shame not to be there. So very interesting what you're doing, and definitely related to the development that we want to include in the ClimaMid for the next task that will be also relate attribution studies to impacts. So yeah, I'm definitely interested in continuing the discussion. And my question, I finished the advertise. I'm also chairing a cost action, a part of a cost action that is the cost action future med. I don't know if you have subscribed for this. I will put the link in the chat. So, and actually the coordinator is Samira Kodayar, who is in Valencia. So I think that's what you presented is completely in the topic of the cost action. And now the question is more related to what you have shown. The thing is, in what you have shown, there are many variables that can be somehow hidden, right? That can influence then your fluxes and can be related to other things that have nothing to do with climate, but can be related, for example, with conflicts, with political choices. So do you plan to, I mean, how can you exclude them? How can you link them so can machine learning do everything, or you need also to interact perhaps with other experts that are also in completely different fields and get input from them? And yeah, so I was thinking of it here. show that I've seen that was this model about everything, that it's a bit what you made me think about. So I would just want to know what you think about that.
Yeah, no, so thanks a lot for the for the website. I will take a look at it. And yeah, thanks a lot for the question. This is like I would say one of the most challenging questions in the field, because actually there are myriads of factors that maybe you have to measure, you have to account for, and then you have to actually say which is the interaction between them. No, so as always about expert knowledge, you always, as much as expert knowledge that you have, that's a plus, because it's guiding you towards where to go. Particularly in our case, it was a data-driven approach. Like we relied fully on statistics. Like you measure correlation between a lot of variables. We gathered 60 variables at first. Knowing more or less which were the drivers in literature, the most common drivers that were appearing, and there you are building your covariates that you can study, and then you keep discarding variables that are not being explained by your models, or that have very increased very low the predictive power, and then you can also and you can do this kind of causal analysis with causal forest, in which actually you have the theory to attribute different impacts towards your target variable. And you can do this in many ways, and you can remove the influence of other variables, but having them constant on this kind of framework, the conditional, which is being used in social science for a lot of time. But first, you need to account for all the confounders. That's all the variables that could influence, that could cause two variables, right? All the observed confounders, they need to be taken into account. And now in the field, you have methodologies that are able to account for latent confounders in data, that are able to extract the presence of latent confounders in your distribution now. So the field is progressing, but of course you need good quality data, a good approach, and algorithms that are fit to your problem. No.
Yeah, but perhaps also expert that tells you what can be the confounders, like confounders in Rwanda might be different than the confounders in Congo.
Exactly. So I was working also in doing causal models of drought displacement in Somalia, and actually goat prices were a very determining factor because of the pastoralist lifestyle there. So actually, from reading literature, it's very hard to get into these variables. So actually, field actors and actors on the ground can give you this information that will help to improve your models. Yes.
Thank you. We can continue the discussion later. Thanks a lot for your seminar.
Thank you. Dim.
Yeah, thanks a lot, Jose. Super interesting. So so my question was also a bit related to your causal method. So you already explained a little bit, but maybe you can say a bit more. What is ultimately your definition for causality?
Mm-hmm.
And maybe also a bit related to the discussion with Davide, like, I mean, we use causal methods basically in two different ways. Either really without any expert knowledge, try to find causal drivers, which we call causal discovery. And then we have what we call causal inference, where we assume, based on expert knowledge, we assume a certain network, and then basically see if the data can fit that network causally, and you can kind of confirm that the data can fit your causal assumptions. And I was kind of wondering if you have if it gets so complex in your case, whether more a causal inference approach is maybe in which helps to introduce more expert knowledge, if that helps. But just a thought.
No. Thank you for the question. And we are doing causal inference. We are not running causal discovery at all. Assuming that these are the causal variables, and then measure the average causal effect, right? Yeah. But Yeah, and with these causal discovery methods, even with causal discovery methods, if you actually fixate some links, they improve a lot. And that's like what you wouldn't want from causal discovery methods, right? But actually, it's really hard when you have all these kind of different distributions, because maybe your algorithm assumes Gaussianity and there are Poisson distributions or skewed distributions in any way, and even not normalizing those can assume the, can fit the assumptions of your method. And yeah, it's a hard problem, especially in this context, no, in the socioeconomic context, where you have so many variables, so many factors.
Yeah. But are you working with partial correlations?
Right now, no. Right now, we are using we use this causal forest approach, and instead of minimizing the mean error like in a random forest, you maximize for the average treatment effect, and then you have your estimates, and then But we use PCMCI in our drop displacement approach, which is another study. Yeah, we know about that. Yeah.
Yeah. Okay, cool. Thanks.
Thanks, Dean.
Any other question? Okay. Well, do you want to add something at this point? Okay. Don't know.
I don't know. If anyone is interested in any of these problems, we are super happy to collaborate or think these things through. So you have my email, I guess, and we can be in contact. And yeah.
Okay. Well, feel free to raise last chance to.
Yes.
Oh, yes, we will share the reference, of course. Okay. So thank you very much. If there is no any other question, we can wrap up now. I just let you know that we have the next session of the XAIDA webinar on April the 9th. So that will be in 3 weeks. Have a good day. Bye, everyone.
Ciao.
Bye-bye. Thanks a lot.
Yeah, thanks a lot. Ciao, ciao.
Thank you.